So yeah, I will present our work on Tactlets, adding tactile feedback to 3D objects using custom printed controls. So digital fabrication has been proposed as a new method for creating customized interactive objects. Prior work has demonstrated input, for example, via touch, deformation, or mechanical controls, but also output, for example, shape-changing interfaces or display output on 3D geometries. So what these approaches have in common is that by printing the custom device, rather than assembling it from conventional electronic components, creating a custom personalized object can be considerably simplified and sped up. So initial work has also explored digital fabrication of haptic feedback using pneumatic actuation. However, higher resolution computer-controlled tactile output at specific locations still largely relies on manually assembling conventional components. Moreover, while these approaches enable fine detailed feedback, the rather large form factors of typical motors and actuators tend to be incompatible with demanding object geometries. So our goal is to enable digital fabrication of high-resolution haptic interfaces for interactive objects of diverse geometries. So to this end, we introduce a novel digital design and fabrication approach for printing custom high-resolution controls for tactile input and output on 3D objects. We call these controls Tactlets. Tactlets are digitally designed and then printed. So each Tactlet comprises individual Taxels that deliver tactile feedback and sense touch. Out of this, we contribute a library of different Tactlet templates, including various types of buttons and sliders. With that, our approach enables a rapid prototyping of haptic interfaces on 3D objects of diverse geometries, based on digital fabrication using either conductive inkjet printing, as in this example, or conductive 3D printing. So in this talk, I want to focus on three main aspects of our work. First, I will introduce the concept of a Tactlet and talk about our contributed library of Tactlet templates. Second, I will provide an overview of our second main contribution, the principle of digital design and digital fabrication of haptic controls. And third, I will provide a summary of our evaluation consisting of an empirical study and 2 application cases. So let's start by looking into what a Tactlet is. So Tactlets are custom fabricated controls for tactile input and output on 3D objects. In this example, a tactile button is placed on the protrusion of the 3D model. Each Tactlet comprises a custom printed arrangement of Taxels, or tactile pixels, which makes Tactlets highly customizable. In this case, the button consists of 5 Taxels that are indicated by black dots. So each of these Taxels senses touch input and delivers tactile output, which allows for high-resolution tactile feedback. In addition to this Taxel layout, a Tactlet possesses an interactive behavior for processing sense touch and controlling the tactile feedback. In this case, the button is activated when it senses being tapped and can deliver a circular tactile feedback when the finger is resting on it. In addition, Tactlets expose high-level properties, for example, whether the button is enabled, and events, for example, when the button is clicked. So with this concept of Taxels as building blocks means that there are many different ways to arrange Taxels and to define an interactive behavior, which in turn allows us to create many different Tactlets controls. So as a starting point for designers and to facilitate the creation of concrete Tactlet controls, we contribute a library of 10 Tactlet templates, which are basically parameterized representations of different Tactlet controls. Based on these templates, concrete Tactlet controls are then instantiated on an object's geometry, similar to how graphical interface controls are instantiated from a class. So let me give you a quick overview of our Tactlet library. For a single Taxel, our Tactlets make use of its touch sensing capabilities and of 4 distinct output states. These states are based on 2 parameters of duration and frequency that enable a large variety of possible tactile output. As a default, a Taxel provides a presence feedback, which allows the user to discover the presence of a Taxel, for example, during ice-free interaction. We implement this as a pulsating output at a low frequency. In addition, we use 2 states of continuous output, a subtle output at a low frequency and strong output at a higher frequency. And last, a Taxel can also be inactive, meaning it doesn't provide any feedback. So let's look at some of the examples of our Tactlet library. We'll start with a simple control based on a single taxel. So this button can be tapped to trigger a click event and delivers presence feedback as tactile output upon touch contact. In addition, the presence feedback can be disabled, for example, to temporarily hide functionality. Adding more taxels allows us to create buttons that offer additional states and more versatile patterns of tactile feedback. One example is the pattern button with 5 taxels as introduced earlier. So it can also be tapped like the regular button, but also allows to provide a circular tactile output pattern when the finger is resting on the button. So this is done by stimulating taxels in one circular direction as illustrated here, and as some of you may have experienced during our demo on Monday. So for buttons, all taxels are typically within the area of one finger pad. Extending the size beyond that allows tactlets that can be actively explored using finger movement. As a basic example, we arrange a series of taxels along a path, for example, a line or curve on the object's surface, which we refer to as tactile sliders. So here's a simple example that allows for rendering a one-dimensional variable. Its current value is rendered as a percentage of taxels that provide strong output, which allows to explore the current state with one finger. While our illustrations here always show a straight line, sliders can, of course, be circular or curved, like we show in this example. So a second example is inspired by traditional mechanical sliders or sliders in graphical user interfaces. It renders its current position as a tactile indicator. So this indicator can be selected by tapping on it and can then be dragged to a new location to change the position of the slider's value. In addition to rendering such active elements, like this indicator, we can also incorporate passive virtual elements. This is illustrated in this last example of rendering virtual tick marks, for example, to support rapid tactile discovery of key positions on the slider. So in summary, I've presented the concept of tactlets and given some examples from our library of Tactlet templates. Please feel free to check out the other templates that we have in the paper. So next, I want to talk about the digital design and digital fabrication of Tactlet controls as one major contribution of our work. So let's start with the design. We contribute a design tool as a plugin for Rhino 3D that allows for high-level design by placing Tactlet controls from our library on the object. After placement, controls can be adapted by moving or scaling them and by adapting high-level parameters. In this example, we design a novel presenter device with haptic feedback, which features a pattern button, an enable-disable button, and a progress slider. So based on the digital design, we want to use digital fabrication to produce a physical prototype. We selected electro-tactile stimulation as a suitable tactile feedback technology to demonstrate our approach. Electro-tactile stimulation is based on electrodes that, when in contact with the skin, can deliver a current to excite mechanoreceptors and trigger a sensation that is roughly equivalent to a vibration. One reason why we chose this technology is that it has been demonstrated to be printable without requiring rigid actuators. A second reason is that it allows to deliver realistic tactile sensations of varying durations and different frequencies. Of note here is that we opted against using stimuli of different amplitude, since amplitude is very user-dependent, and instead calibrated to intensity of a comfortable level. All right, so one of the important aspects of electro-tactile stimulation is that it requires touching 2 electrodes to deliver tactile feedback. That means that from our abstract Taxel-based design, we first need to generate a concrete electrode layout. So in a nutshell, we do that by creating one electrode at each taxel's location and then using either close-by electrodes from other taxels as ground or creating a dedicated ground electrode. And now, since the user is always touching 2 electrodes at one taxel location, we can also easily sense touch using a resistive sensing scheme, which is time multiplexed with actuation. So based on the generated files, we can then fabricate the physical interface by simply 3D printing it with embedded electrodes using conductive filament. As an alternative for even more rapid prototyping, interfaces can be printed using conductive inkjet printing. They are then simply cut out and attached to the target object, which is, in this case, a 3D printed version of the controller model. For both techniques, the result is then connected to the Tactlet's hardware controller. So with that, we have a first working prototype. In this example, we use tap events on the buttons to control a slideshow and deliver progress information via a tactile progress slider. The upper button further provides the circular tactile feedback based on predefined slide timings. Now, if you want to iterate on the design, a typical way is to go back to the digital design and to repeat the process. As an alternative, we introduce a real-time design mode to support rapid hands-on testing and design refinements using the printed prototype. So in this mode, the design tool and the fabricated prototype are connected and synchronized in real time. So to physically explore design options, the design tool offers live control of the prototype's interactive behavior. In this example, the tool visualizes the touch input and offers control to change the pattern speed or to set the activated-deactivated state of the selected pattern button. We consider this a critical feature as tactile feedback cannot be adequately conveyed through a rendering in a design tool, but instead needs to be physically experienced. So in addition, the design tool allows for hands-on refinement of the design by using the input capabilities of the fabricated prototype. Instead of switching back and forth between the physical prototype and changing parameters in the graphical user interface, the designer can change properties of the Tactlet directly on the physical object. In this example, the designer sets a new length of the slider by first selecting a start taxel and then a second corresponding end taxel. The tool then immediately updates the length of the slider as is indicated on the right by the two deactivated taxels on top. So with that, I have presented our second main contribution. Last, I want to give a very brief overview of our evaluation. So our evaluation consists of two parts. One is an empirical evaluation, and the other one is two application cases. I will not go into details of the empirical evaluation here, but in a nutshell, we focused on confirming the feasibility of electro-tactile stimulation on non-planar geometry, which is one specific point for a technology that has otherwise been very well studied in prior work. You can find the details in the paper. For our application cases, we have already seen the presenter with tactile feedback in earlier examples. Our second application case was inspired by haptic edge displays. We aimed to prototype and explore a similar tactile interface on the edge of a smartphone while leveraging the benefits of our approach, which is a slimmer form factor, compatibility with curved geometries, and rapid design iterations. So we first prototyped an input slider that renders virtual tick marks on the curved back edge of the phone case. In this example, to scroll through a PDF while dynamic tick marks indicate sections in the current open document. We then tested the design and wondered whether the same interaction was possible using the curved top edge of the smartphone. We designed and printed a fitting smaller slider, but found that the space was too small for scrolling documents. We then quickly changed the behavior to a progress slider and found this to be a more suitable interaction. One example would be for quickly checking your phone's battery level with one finger without taking it out of your pocket. So then last, in the third iteration, we explored the phone's back as one promising location for a slider. We prototyped a curved slider placed on an indent around the phone's fingerprint reader. We found this design to be promising for scrolling documents while looking at the screen, but also as a progress slider when the phone is in one's pocket. So satisfied with our three iterations, we actually 3D printed the phone case with embedded electrodes. So with that, I have presented our evaluation that demonstrates the feasibility of the Tactlets approach. Last, I want to briefly talk about one point of future work. So the one major factor for future work that we plan exploring is actually exploring different printed actuation technologies. For example, printed mechanical actuators based on electroactive polymers like shown in this video. So we see two important aspects of investigating such technologies. First, they could allow to overcome the limitations of electro-tactile stimulation, for example, the need to calibrate the intensity or the requirement of touching two electrodes to receive stimulation. And second, we believe that they will allow us to demonstrate that our main contributions of the Tactlets concept, the digital design process, and the Tactlet templates generalize beyond our implementation using electro-tactile stimulation. So in summary, I have presented our work on Tactlets. I've introduced the concept of Tactlets as custom-printed, high-resolution controls for tactile input and output on 3D geometries, and provided examples from our Tactlet library. I've introduced our contributed digital design and fabrication process for haptic controls, including a novel real-time design mode. And I have presented results from our evaluation that verify the functionality of the Tactlets approach. With that, I conclude my talk, and I'm happy to take your questions.
Talk was perfectly timed. I can't believe it. It was down to the second. 15 minutes.
Yeah,
Were
practice.
you using Tactlets to signal your timing?
I wanted to, but yeah.
Okay, do we have any questions? Okay, I have one. So you're using a technology here, and I think this is true of future technologies that you've suggested you might use for this, which is not electro-tactile, it can stimulate you when you're not moving, so you can experience it passively as well as actively, depending on the measurement. But if you're using it as an input modality, if I wanted to, so we have the concept of anchors, right, in physical UIs, where I can, like you have, when you're typing on a keyboard, some of the keys have little bumps on them so you can put your hand in the right place. And so sometimes a flat, smooth interface that you're using without eyes, it can help to have a physical anchor that you can feel where your hand is. In this case, how do you have, like if I want to make a selection, if I want to give a gesture, a control gesture, how do I separate that from the anchoring function of I'm using the stimulus to tell me where I am on the device? Do you have any idea of how you design the interaction that way?
Well, that's one of the main limitations of this work, which is basically the Midas touch problem. So, like, when we touch it, we cannot really distinguish whether this is like exploration, so the user is just exploring and trying to get haptic feedback on where the controls actually are, or the user is actually touching to select something. So what we do in our current design is we just use tapping, so it's basically timing-based differentiation between the two, but of course this is not optimal. So we would really like to use something that offers different capabilities like hovering or force input, so then maybe that way we can better distinguish between exploration and providing haptic feedback, and then also selection.
Okay, so for that you would need some additional sensing modality, like, for example, force, pressure sensitivity or hover.
Yeah, we think that this is probably a good way to explore, which with the EAPs would probably also be possible to integrate it. Yeah. With the current implementation that we have, we could add something like capacitive sensing so that we have some approximation of pressure, or at least a hover state as an additional state.
Okay, thank you. Any other questions? Okay. Last chance.